Okay, let's continue the lesson. Now, before we do this further, you have to remember what are in these brown boxes. These definitions are very important. Whatever is in this brown box should be memorized with understanding, because in the exam they can ask you to write what it is. So here you can see what is binding energy. Now this definition may not be very complete, but most of the definitions are very complete. Okay, the minimum energy needed to pull a nucleus apart into its separate nucleons to infinity, okay, is known as binding energy of the nucleus. So the nucleons are protons and neutrons. So to separate them, you will need energy, and you have to separate them to infinity. So that has to be added to the definition, and you can also go through the glossary of the book that also has certain definitions. And when you go through some question papers and mark schemes, you will see what exactly they are looking for. But 99% of the time or 90% of the time these definitions are sufficient. But I have also told you all to go through the study the definition here as well as the definition or the meaning of the word in the glossary. For example, you can see this word is in green bold letters, which means the meaning of that will most probably be in the glossary also, which is at the back of the book. Okay, so if I go to the glossary and if I look for binding energy, you can see it's here. But see, minimum external energy required to separate all the neutrons and protons, those are the nucleons of a nucleus. But again here it doesn't say infinity. But when we went through some mark schemes, I have discussed the latest 2019 papers also, or even the 2020 papers, you can see there was a question on this. They had asked you to write what binding energy is, and in that I explained this in detail. Okay, so in this chapter this is what is left. Now before we start this, let's quickly go through what we learned in the previous video or previous lesson. So we started here, this is the beginning of the chapter, and these are very important. Whatever is in these green boxes or highlighted in green are very important. You have to understand them very well. So we had that, and remember in the exam paper also they can give you this kind of graph and ask you to find what is the element or nucleon number, proton number, when it undergoes an alpha decay or beta decay, beta plus, beta minus, like that. So you have to know this to do that. Then also we went through mass defect. Mass defect is also called mass deficit, and here you can see again this is in a green box. Mass defect of a nucleus is the difference between the total mass of the individual separate nucleons and the mass of the nucleus. So a nucleus is made up of protons and neutrons. Then if you take the mass of the nucleus, that will be one mass, compared to if you add the masses of the protons and neutrons separately that make up that nucleus. So that difference in the mass is called the mass defect. Okay, so you can see here, if you do this is the mass of a proton, this is the mass of a neutron. You can see the mass of a neutron is a little bit higher than the mass of a proton. And in the carbon nucleus, carbon 12 nucleus, 12 minus 6 is 6, which is the number of protons. So this has neutrons. This has 6 neutrons and 6 protons. The mass number minus the proton number will give you the number of neutrons. So if you multiply this by 6, and if you multiply this by 6 and add them together, you will see that number is not the same as this number. So if you get the difference between those two, that one and this, then you can see that will be the mass defect, or mass, also called mass deficit. And here this is already showing you that. So individually if you add the protons and neutrons, the mass will be greater. You can see on this scale this side is down, that means this is heavier than this. So if you take the individual nucleus, it will be lighter compared to the masses of the protons and neutrons. If you add them, that make up that nucleus. Okay. And in the previous lesson I explained why that is. Anyway, now the next one also we went through this. So mass excess, see, mass in U minus nucleon number, that is mass excess. Here you can see yeah, so we get that example here. Now this is also important. Then something very important here is this. Now you can see this is the binding energy per nucleon. That is, if you divide the binding energy by the number of nucleons in that particular nucleus or atom, that will give you the binding energy per nucleon. So for example, if you find the binding energy of carbon 12, and if you divide that value by 12, that will give you the binding energy per nucleon, because there are 12 nucleons in carbon 12. Okay, and something that you can observe here is that iron has the highest binding energy per nucleon. After that it decreases. So this side also it decreases. If you go this way it decreases, if you go this way it decreases. So this has the highest binding energy, so the bi value decreases. So when the nucleon number increases up to iron, the general trend is that the binding energy per nucleon increases, and after iron the general trend is that the binding energy per nucleon decreases. So you have to remember this. So if it's somewhere down here, you can see it's always less than something up here. Similarly over here, if it's somewhere up there, it's clearly greater than something down here. Now in both fission and fusion reactions, you have learned that energy is released. In both the fusion as well as the fission reactions, you have learned that energy is released. So how come energy is released in both nuclear fission and nuclear fusion? Now in nuclear fusion, what happens? The nucleons fuse, or they get together and form a bigger nucleus. That is nuclear fusion. In nuclear fission, what happens is the nucleus breaks, or it disintegrates. Then it gives smaller, or we can say it gives a daughter nuclei. It gives a smaller nucleus. So that is nuclear fission. But nuclear fusion, the nucleons get together and form a bigger nucleus. So what you can see here is, now it's shown in this graph. So this way, from elements starting from hydrogen all the way up to somewhere there, fusion occurs. But for the elements on this side of iron, fission is occurring for them. Okay, so from here to here fusion, that way fission, and that is what is explained here. So we can go through some of these examples. I think it's easy to understand also. Calculate the binding energy per nucleon of iron. Now mass of neutron is given, mass of proton is given, then mass of the iron nucleus is given. So first we can find the mass defect. Okay, so to do that, first we will have to find the number of neutrons in iron. That is 56 minus 26, 30. 30 neutrons are there in iron. Then 30, which is the number of neutrons, times the mass of one neutron, which is this. This will give you the mass of the neutrons separately, 30 neutrons separately. Then 26 protons are there, therefore 26 times this will give you the mass of protons, if you consider them separately, not in the nucleus together but separately. Okay, so that will be that. And then to find the mass defect, what we do? We take the difference between that. Now remember, if you consider them individually and add them together, that mass will be greater than the mass of the nucleus. So it will be this minus the mass of the nucleus, which is that. So we have this. Okay, then this is the mass defect. Now once we have the mass defect, we can find the binding energy of the nucleus. And after we find that, we can divide it by the number of nucleons to find the binding energy per nucleon. So you can see here, determine the binding energy of the nucleus. Binding energy, we will use this equation, mc square. M is the mass defect, which we found here, that is the mass defect. Then c is the speed of light, so c squared. Then we have this is the binding energy. Then binding energy per nucleon is this divided by 56. So that is the answer. Okay, now here you can see what I said before is explained. For nuclides with A, approximately there is not much variation in binding energy per nucleon with A greater than 20. So here you can see 20, that is the nucleon number. So if you go up here, so somewhere there. So here, when it's greater than 20, there isn't a much difference in the binding energy. But here you can see hydrogen, helium somewhere there, lithium is somewhere here. So there's a big difference. But over here, after the nucleon number or mass number is greater than 20, there isn't much of a difference. But you can see from here to here, nucleon number 1 to nucleon number 2, there is a big difference. The greatest value of binding energy per nucleon is found for iron, and I told you before that iron is right at the top there. So binding energy per nucleon is highest for iron. Iron 56. This isotope of iron requires the most energy per nucleon to dismantle it into separate nucleons. Previously we learned the definition of binding energy. So binding energy highest means it will require the most energy per nucleon to dismantle it into separate nucleons. Hence iron 56 is the most stable isotope in nature. Okay, I hope that's clear. You should know this. Now so that is the pattern. Okay, you have to understand this graph, very important. This graph shows the binding energy per nucleon for a number of nuclei. The nucleus becomes more stable as the binding energy per nucleon increases. So iron is having the highest, therefore it is the most stable, and that's why you can see over here, hence iron 56 is the most stable isotope in nature, and therefore iron requires the most energy per nucleon to dismantle it into separate nucleons, because the binding energy for it is the highest. Then I told you about fission and fusion. Now we will see what happens. Binding energy, fission and fusion. We can use the binding energy graph to help us decide which nuclear process, fission, fusion or radioactive decay, are likely to occur, and that is shown here. So we have fission, fusion and radioactive decay. You have to know the difference between them. So in fission, what happens? The nucleus breaks because a neutron is absorbed, and when the neutron is absorbed, that causes the nucleus to become unstable, so it disintegrates or breaks into two nuclei, let's say, and that gives more neutrons, and those neutrons collide with other neighboring nuclei, and they get absorbed by those neighboring nuclei, and then it continues. And this is what happens in a nuclear reactor. When we learned about the nuclear reactor, we have learned this. Okay, so you can see here, fission is the process in which a massive nucleus splits to form two smaller fragments. So two smaller fragments, fission, rather than simply emitting alpha or beta radiation. Now, remember in decay, we got alpha radiation, beta radiation, like that. That was in radioactive decay. So we saw what happens in beta minus decay, beta plus decay, and also in alpha decay. So that is different from fission. Okay, so fission splits into two smaller fragments rather than simply emitting alpha or beta radiation. For uranium, A is equal to 235, that is the nucleon number, also called the mass number, and the typical fragments have A equals 140 and 95. Now previously we have learned about this even in the O-level class. You can see the lessons on that to have a better understanding. If we look at the binding energy curve, we see that these two fragments have greater binding energy, less potential energy per nucleon than the original uranium nucleus. So uranium is somewhere there. If you look at the graph here, it's 235. So somewhere there, uranium 238, 235, they are isotopes. Anyway, both of these isotopes are down on the right side. So, but this 140 and 95, you can see it's somewhere here, right? 95 is somewhere there, then the other one is somewhere here. So they clearly have greater binding energy. Hence, if the uranium nucleus splits in this way, energy will be released. Okay, so the fragments have more binding energy. That means if the uranium nucleus splits in this way, it will release energy. Both fusion and fission are processes that tend to increase the binding energy per nucleon of the particles involved. So both of these, now you can see when fusion occurs, what happens? The nucleus becomes bigger, right? Rather not bigger, the nucleon number increases. So you have to be very careful with the words also. If you say bigger, some mark schemes won't accept that. You have to say the nucleon number increases. So when the nucleon number increases for the elements here, the nuclei here, when they become bigger nuclei, you can see the binding energy also increases. So when fusion occurs, what happens? The binding energy per nucleon increases. But when fission occurs, also the binding energy per nucleon increases. Now they gave you the example of uranium 235. So uranium 235 is somewhere there, but the fragments of it are somewhere here. So now you can see it has gone up the curve. The binding energy has increased. Similarly, in fusion also, when fusion occurs also, binding energy increases. So in both cases, because the binding energy increases, in both cases energy is released. Both fusion and fission processes that tend to increase the binding energy per nucleon of the particles involved are processes that tend to increase the binding energy per nucleon involved. Okay, then fusion is the process by which two very light nuclei join together to form a heavier nucleus. In the reactions that occur in the sun, hydrogen nuclei fuse to form helium nucleus. This is the process by which energy is released in the sun, when hydrogen nuclei fuse to form helium nuclei. If two light nuclei fuse, the final binding energy per nucleon will be greater than the original value. The high binding energy or low total energy of the helium for nuclides means that it is rare for this nuclei to fuse. Now this has a high binding energy, so that means it's more stable. Okay, so it was here, then it went up there. Remember, if you see this graph here, hydrogen is here, helium is somewhere there. Higher binding energy for helium. So that it is rare for this nuclei to fuse. Okay, so that is that part. I think this part is also clear. So you saw the red dot, the more red dot, that is for iron, has the highest binding energy per nucleon. See, you will see that the general trend is for light nuclei to have low binding energies per nucleon. See over here it is less, but for these it is higher than these here. Note however that helium has a much higher binding energy than its place in the periodic table might suggest. The high binding energy means that it is very stable. Other common stable nuclide include carbon 12. So you see carbon is also up there, helium is somewhere there. Oxygen 16. So you see it's also somewhere there. And you can see some pattern here. For chemistry also you would have learned some details about this. Okay, which can be thought of respectively as 3 and 4 alpha particles bounded together. So alpha particle is identical to a helium nucleus. So if you put two helium nuclei together, then you can see the proton number of this helium is 42. So then 2 plus 2, 2 plus 2 plus 2, 2, 4, 6, 4, 8, 12. Then it will give you this. Then if you put 3 helium nuclei together, you get carbon 12, right? Similarly, if you take 4 of them and put together, you get this oxygen. That's what they're saying. Okay, so we went through this part. More stable nuclei are formed when alpha particles are bounded together. Now here remember this point, carbon 12, oxygen 16. The alpha particles do not remain separate as shown here. Rather, the protons and the neutrons are tightly packed together. This is just to show you that 3 or 4 of them, but it's all one thing together. There are no spaces like this. Okay, it's all together. That's what they're saying. This is to show you that 3 of them here are here, 4 helium nuclei are there, but it's all together. This is to show you the stability. Okay, they are more stable when you have alpha particles pairs or like this bonded together. Okay, so then next one is randomness and decay. Okay, now before we start this topic, I will quickly tell you the important points here. So then later after that we can go into the detailed explanation. Like over here I explain, so you have to know this. Okay, then the calculations are very important like this, and also here you can see the steps are listed. When you want to find the binding energy per nucleon, you have to use the equation equals mc squared, where m is the mass defect. So first you have to find the mass defect, that is the mass of the nucleons separately when you calculate that, minus the mass of the nucleus, the mass of the nucleons that make up the nucleus. If you take the individual masses and add them together, and that result, if you minus that result minus the mass of the nucleus, the mass of the nucleus is lighter than the mass of the individual neutrons and protons together. So that difference will give you the mass defect. Then mass defect times c squared will give you the binding energy. And if you want to find the binding energy per nucleon, you divide it by the number of nucleons. We went through an example over here. This example is very important, and you have to also answer all these questions. Okay, so after every topic you can see there are some questions. So these questions are based on what you learned here in this topic. So make sure you do them, and you have to answer all the questions in the brown boxes and check the solutions. Then you will have a good understanding of that particular chapter or topic. Okay, so here also I will first show you the important points. Now they can, in the exam papers I have seen them asking, what is this spontaneous decay, what is randomness? You have to be able to explain that. These are very common questions in the exam. And also you can see the decay constant. Now over here this is a constant, so there is an equation with this. Now this is the unit of activity. Again you can see what is decay constant. They can ask you the probability that an individual nucleus will decay per unit time interval is called the decay constant. So these are very important in the exam papers. They can ask you to write this down. What is decay constant? What is activity? Activity A of a radioactive sample is the rate at which nuclei decay or disintegrate. Now again I told you whatever is in the brown boxes is very important. The unit of activity is BQ, becquerel. Becquerel is equivalent to per second. Like you know, hertz, frequency has the unit hertz. Hertz is equivalent to the unit per second because it's the number of cycles per second. So over here it is the number of decays per second. So it's like hertz is to per second, becquerel is to per second. Then using this to, we can see, and we also know the activity is proportional to the number of nuclei. So with that we can write A is proportional to N, and that constant is the decay constant. So then we write this. Now yeah, so activity is also equal to delta N divided by delta T, because that is what activity is, right? So you have seen this. Now we will see the details after. Then again these equations are very important. In the exam you have questions where you need to use these equations and do the questions. So, and also here these definitions. The half-life of a radioactive isotope is the mean time taken for the half of the active nuclei in a sample to decay. So when that becomes half, the activity also halves because lambda is constant. So when n halves, the activity also halves. So again, the half-life of a radioisotope is the mean time taken for half of the active nuclei in a sample to decay. Then we have this equation. Can show you the derivation of this also, but for now I think this is sufficient. Okay, so you can see here there is a minus there. This number is positive but the power is negative, which means if you plot a graph of this n versus t, okay, it will be a exponential decay curve. It will be decreasing like this. The gradient will be the magnitude of the gradient will be decreasing. Okay, so same thing you can do with activity, because n is proportional to a. The activity is proportional to the number of undecayed nuclei. Okay, then afterwards over here you can see that there is a way to determine the half-life. This is the next page. Okay, see the next page. So you should know this. Now here there is an example. We'll go through that. And yeah, so you see, you have to use that equation, and then we also get this. Okay, so here you have an equation which is relating the decay constant to the half-life. Lambda is equal to this over this. Okay, then the summary. So you can see the equations. ln2 is actually equal to this. So here you saw this number, that is equal to natural logarithm of 2. Now in the exam papers also, this is a equation that you have to use again and again. In several exam papers I have seen this question. Okay, so that being said, now we can actually start the rest of it in detail. But these are the main points. So even once you know these points, you can answer the questions. Alright, so listen to a counter connected to a Geiger-Müller tube that is detecting the radiation from a weak source, so that the count rate is about 1 count per second. So you'll hear the sound. Each count represents the detection of a single alpha particle or beta particle or a gamma ray photon. So see, each count represents, because when that alpha particle enters, then it will cause ionization, and as a result you will get this sound. Okay, so for more details you can see how the Geiger-Müller tube works when detecting radiation. You will notice that individual counts do not come regularly, so that's why we have this. Okay, so here count rate showing randomness of decay. You will notice that the individual counts do not come regularly. The counter beeps or clicks in a random irregular manner. If you try to predict when the next click will come, you are unlikely to be right. You can see the same effect if you have a rate meter. So we have the Geiger-Müller tube or the rate meter. Geiger-Müller connected to the counter or to the rate meter. You can see the same effect if you have a rate meter which can measure faster rates. Figure 31.7. So here you have the source of radiation, and this is the Geiger-Müller tube. So the radiation goes in this, and then remember in the O-level class you would have learned about the parts and what happens. Then you will get some reading there. The time constant of this rate meter can be adjusted to smooth out rapid fluctuations in the count rate. So you have something like this, and then you can use the settings here and adjust the settings so you get a proper curve, like smooth one. Okay, the needle fluctuates up and down. Usually rate meter has a control for setting the time constant, the time over which the meter averages out fluctuations. Usually this can be set to 1 second or 5 seconds. The fluctuations are smoothed out more on the 5 second setting. Figure 31.8 shows a graph of count rate against time with a smoothing of a few seconds. The count rate decreases with time as the number of radioactive nuclei that are left decreases. So remember, the activity decreases with the decreased number of radioactive nuclei remaining, because what happens is the nuclei decay and they go off. So when they decay, there are no more nuclei of the radioactive sample. So the number of radioactive nuclei decrease when the decay is happening. So as a result, the activity also decreases. The count rate also decreases. The fluctuations either side are caused by the randomness of the decay. Now you can see here it's not a smooth curve. There are fluctuations. Now why are these fluctuations? You have to remember this. The fluctuations either side are caused by the randomness of the decay. Now in the exam, this is a possible question. So it is apparent that radioactive decay is a random, irregular phenomenon, but is it completely unpredictable? Well, not really. We can measure the average rate of decay. We might measure the number of counts detected in 1000 seconds and then calculate the average number per second. We cannot be sure about this average rate either, because the number of counts in 1000 seconds will fluctuate too. All out measurements of the radioactive decay are inherently uncertain and imprecise, but by taking average over a sufficiently long time period, we can reduce or smooth out the random fluctuations to reveal the underlying pattern. Okay, so again, I think it's self-explanatory. Okay, so we can find the pattern. Now remember, this was about randomness, and here was an important point. Fluctuations here are caused by the randomness of the decay, and over here you see that by taking averages over a sufficiently long period of time, we can reduce or smooth out the random fluctuations to reveal the underlying pattern. Then spontaneous decay. Now this is also very important. Whenever there is a nuclear decay question, this is a possible topic that can be tested, that has been tested. Radioactive decay occurs with the unstable nuclei of an atom. A nucleus emits radiation and becomes the nucleus of an atom of a different element. This is a spontaneous process, which means that we cannot predict for a particular nucleus when it will happen. So for example, if you take a piece of uranium, it is made up of uranium atoms, but we don't know which uranium atom will decay next. That is what this means. So maybe there are a million or a billion uranium atoms, but we don't know out of those million, billion or thousand, which one will decay next. If we sit and stare at an individual nucleus, we cannot see any change that will tell us that this is getting ready to decay. And if it doesn't decay in the first hour, when we are watching it, we cannot say that it is any more likely to decay in the next hour. So this is what I explained. What is more, we cannot affect the probability of an individual nucleus decaying, for example, by changing its temperature. Okay, so this was a question that was asked in the exam. So they had asked whether the temperature will affect the decay. So the answer is no. So we cannot affect the probability of an individual nucleus decaying, for example, by changing the temperature. Now these things you can note down. Okay, so what is spontaneous decay and what factors do not affect that. Okay, and we cannot predict. We don't know which nucleus will decay next. This is slightly odd because it goes against our everyday experience of the way things around us change. We observe things changing. They gradually age, die, rot away. But this is not how things are on the scale of atoms and nuclei. Many of the atoms of which we are made have existed for billions of years and will still exist long after we are gone. The nucleus of an atom does not age. Okay, so nucleus of an atom does not age, but we age. If we look at a very large number of atoms of a radioactive substance, we will see that the number of undecayed nuclei gradually decrease. However, we cannot predict when an individual nucleus will decay. So again the same thing. Each nucleus makes up its own mind when to decay, independently from its neighbors. This is because neighboring nuclei do not interact with one another, unlike neighboring atoms. So here is another point. So we don't know which nucleus will decay because neighboring nuclei do not interact with one another, unlike neighboring atoms. So here nuclei do not, but atoms, you know, they can interact between them. The nucleus is a tiny fraction of the size of the atom, and the nuclear forces do not extend very far outside the nucleus. So one nucleus cannot affect a neighboring nucleus by means of nuclear force. Being inside, so again you can write these are factors that do not affect. So we don't know which nucleus will decay. Being inside the nucleus is a bit more like living in a house in the middle of nowhere. You can see just see out into the garden, but everything is darkness beyond, and the next house is 1000 kilometers away. So like you all think like you are a nucleus, you're in a house, and the next house is 1000 kilometers away, so you don't have any kind of like influence on the other house. The fact that individual nuclei decay spontaneously and independently of their neighbors and of environmental factors account for the random pattern of clicks that we hear from a Geiger counter and the fluctuations of the needle of the rate meter. To summarize, nuclear decay is spontaneous because the decay of a particular nucleus is not affected by the presence of other nuclei. Very important, okay? The decay of nuclei cannot be affected by chemical reactions or external factors such as temperature and pressure. Nuclear decay is random because it is impossible to predict when a particular nucleus in a sample is going to decay. Now previously we saw this spontaneous, so here you can see which is spontaneous because of this. In the exam they can ask you this. They can also ask you what is spontaneous. Then you can write these things also down. Then random, why? It is impossible to predict when a particular nucleus in a sample is going to decay. Each nucleus in a sample has the same chance of decaying per unit time. Okay, so we discussed that over here. Alright, mathematics of radioactive decay. We have seen that radioactive decay is a random, spontaneous process. So here we saw random and spontaneous. Because we cannot say when an individual nucleus will decay, we have to start thinking about very large number of nuclei. Even a tiny speck of radioactive material will contain more than 10 to the power 15 nuclei. When we can talk about the average number of nuclei that we expect to decay in a particular time interval, in other words, we can find out the average decay rate. Okay, so here you can see average number of nuclei that we expect to decay in a particular time interval. That average decay rate. Although we cannot make predictions of the individual nuclei, we can say that certain types of nuclei are more likely to decay than others. For example, a nucleus of carbon-12 is stable. Carbon-14 decays gradually over thousands of years. Carbon-15 nuclei last on average a few seconds. So from this we know that we can say the half-life. Okay, so because of the spontaneous nature of the radioactive decay, we have to make measurements on very large numbers of nuclei and then calculate averages. One quantity we can determine is the probability that an individual nucleus will decay in a particular time interval. For example, suppose we observe 1 million nuclei of a particular isotope. After 1 hour, 200,000 have decayed. Then the probability that an individual nucleus will decay in 1 hour is 0.2 or 20%. So 1 million, and out of that 200,000. So if you divide this number by 1 million, you will get 0.2, and if you convert to a percentage, 20%. So therefore the probability that according to this, okay, over here what we saw, according to that, if in 1 hour out of 1 million nuclei in a particular radioisotope, out of that, if 200 decay in 1 hour, then the probability that an individual nucleus will decay in 1 hour is 0.2 or 20% when you convert this to percentage, since 20% of the nuclei have decayed in this time. That means out of 100, if you have 20 will decay in 1 hour. Of course, this is only an approximate value, since we might repeat the experiment and find that only 199,000 decay because of the random nature of the decay. So approximately 200,000 out of a million, for example, because of the random nature of the decay. The more times we repeat the experiment, the more reliable our answer will be. We can now define the decay constant. The probability that an individual nucleus will decay per unit time interval is called the decay constant, lambda. So for the example above, we have decay constant is 0.2 per hour. Now why 0.2? Because out of a million, 200,000 decay. So therefore in 1 hour it will be 200,000 divided by 1 million, which is 0.2. So we have what we call now the decay constant. We can now define the decay constant. What is the decay constant? This is very important. You have to memorize it with understanding. The probability that an individual nucleus will decay per unit time interval is called the decay constant, lambda. For the example above, we have decay constant lambda equals 0.20 per hour. So it's very easy. You see, once you understand this, it's easy to memorize it with understanding. Probability that an individual nucleus will decay per unit time interval. So that time interval can be per hour, per second, per minute, for example. So that is called the decay constant. Note that because we are measuring the probability of decay per unit time interval, lambda has unit per hour, per second, like that. But if it's per second, the unit is becquerel. Okay, the SI unit is actually per second becquerel. This is SI unit. The activity of a source is defined as follows. The activity of a radioactive sample is the rate at which nuclei decay out. Sorry, this is the unit of activity. Okay, so decay constant, you can't write it as becquerel. Activity, the unit is becquerel. Decay constant is per second. Okay, so be careful with that. Activity is measured in decays per second, and activity of one decay per second is equal to 1 becquerel. The symbol we use for activity is capital A. The symbol we use for decay constant is lambda. Clearly, the activity of a sample of the decay constant lambda of the isotope under consideration. Clearly, the activity of a sample depends on the decay constant. So then we have this. So you see, n is the number of nuclei. So we don't have a unit for that, but this has the unit per second. So therefore, A will have the unit per second, but that per second we can also write it as becquerel, which is the unit of activity. But lambda we don't write it as becquerel because for lambda the unit is per second. The greater the decay constant, what is decay constant? The probability that an individual nucleus will decay per unit time interval, the greater is the activity of the sample. So greater the lambda, greater the A. The greater is the activity of the sample. It also depends on the number of undecayed nuclei n present in the sample. For a sample of n undecayed nuclei, we have, okay, so very important equation. We can also think of the activity as a number of alpha or beta particles emitted from the source per unit time. Hence, we can also write the activity as delta n divided by delta t, where delta n is equal to the number of emissions or decays in a small time interval or particular time interval, delta t. So you have two equations. One is this and the other is this for activity. So there are two equations. You can note these two down. The exam, they can test you on these equations and they can ask you what is activity, what is lambda. So to understand this better now, let's go through an example. Through two examples. A radioactive source emits beta particles. It has an activity of 2.8 into 10 to the power 7 becquerel. You see, the unit of activity, SI unit is becquerel, which is equivalent to per second. But lambda also has this unit per second, but there the unit is not becquerel. Estimate the number of beta particles emitted in a time interval of 2 minutes. State one assumption made. Okay, so we have been given the activity. We have been given the time, and they're asking the number of beta particles emitted in a time interval of 2 minutes. Okay, so we can find n. So we can write the quantities that are given in SI units. We can write them down first, and then you figure out which equation you need. So you need to find n, right? That means the equation that we will have to use is this, because it has all three quantities. So activity is given. So for activity you have learnt only two equations and you are given the time. Therefore this is the equation you are going to use, because this you can't use. You don't know that you don't have a unit for time. Quantity for time here. I mean, you don't have the time quantity here. You have it here. So that's why you use this equation. So when you are given a question, for example, if it is activity, then you have learnt only two equations. So then you can remember those two and then figure out which equation to use. So now you can use that. You will get the answer 3.4 into 10 to the power 9. Now this doesn't have a unit because it's the number of nuclei remaining. Okay, because we have to consider the nuclei remaining. Actually this n is the nuclei. So we have assumed that the activity remains constant over a period of 2.0 minutes. Okay, so the activity is equal to delta n over delta t. Now we have to determine the number of beta particles emitted. Then delta n is equal to a delta t. What is a? This is given here. Then t is also given. So we can find delta n, the number of beta particles emitted in that time interval. Okay, and also over here we can see that when n decreases, a decreases, but the problem is over here it is delta n, the change in the divided by delta t. So here it is delta n, but here it is just the n, because n here, actually here it is the undecayed nuclei, but here this is the number of emissions. So again be careful with that. So this is the number of undecayed nuclei in this equation. Here that n is different. This is equal to the number of emissions or decays in the particular period of time. Okay, so finally this is assumed that the activity remains constant. We have assumed that the activity remains constant over a period of 2 minutes. So this activity, yeah, we assume it's constant, then only we can do it. So that's why we have to assume it's constant and do it. Anyway, a sample consists of 1000 undecayed nuclei of a nuclide whose decay constant is this. Determine the initial activity of the sample, estimate the activity of the sample after 1.0 seconds. So again, you can write the quantities that are given in the question and figure out which equation to use. So this is the number of undecayed nuclei. Now which equation has that? This one. So the equation that has activity and undecayed nuclei is this. This is the number of emissions or decays. Okay, so this n and this n, they are different. Okay, then we have this. Now we are also given the decay constant, and only one equation you have learned that has the decay constant. Therefore this is the only equation we will have to use. So substitute, you will get the answer 200 becquerel activity, then n is 1000, that is the initial activity. Then estimate the activity of the sample after 1 second. Okay, so after 1 second we might expect that 800 nuclei to remain undecayed. The activity of the sample would then be, yeah, so 200. Okay, so this was the initial activity. Determine the initial activity of the sample. Initially this is the number of undecayed nuclei. The decay constant is this. So so this is the initial activity. But after 1 second, now you can see 200 becquerel, then that is the activity. Then we have 1000 undecayed nuclei. So after 1 second, what happens? That activity, 800 nuclei have gone. So 800 nuclei remain. Now again remember, this n is the number of nuclei remaining. So we will use that here. Now decay constant doesn't change, but n changes, and when n changes, a changes. So we get 160 becquerel. In fact, it would be slightly higher than this, since the rate of decay decreases with time all the time. Less than 200 nuclei would decay during the first second. The next topic is count rate. Although we are often interested in finding the activity of a sample of radioactive material, we cannot usually measure this directly. This is because we cannot easily detect all the radiation emitted. Some will escape past our detector, so not all the radiation enters the detector or Geiger-Müller tube. Some will escape past our detectors and some may be absorbed within the sample itself. A GM tube placed in front of a radioactive source therefore only detects a fraction of the activity, because it detects only a certain, it doesn't detect all the radiation. The further it is from the source, the smaller the count rate. Therefore our measurements give a received count rate R. that is significantly lower than the activity A. If we know how efficient our detecting system is, we can deduce A from R. If we know how efficient our detecting system is, we can deduce A from R. Now what is R? That is the received count rate. A is the activity. So the activity is higher than the count rate. Okay, because when it comes to the count rate, only a certain amount of radiation is detected from the total radiation emitted. If the level of background radiation is significant, then it must be subtracted to give the corrected count rate. Okay, so remember we also have background radiation. So this will give us the background count rate. That means when there is no sample of radiation, there will still be a reading on the detector. So anywhere you do it, there will be a reading even without a radioactive source, because of the nature emitting radiation. Okay, radon gas that gives out radiation, so that will be detected, and that will be the background count rate. You have learned this before, I think, in the O-level class. Okay, then we have decay graphs and equations. Now we will see about the corrected count rate also. And by the way, you have to answer all these questions. They are very important. So it is based on what we have learned here. Okay, next topic, decay graphs and equations. The activity of a radioactive substance gradually diminishes as time goes by. The atomic nuclei emit radiation and become different substances. The pattern of radioactive decay in a sample of a very important pattern found in many different situations. The pattern of radioactive decay is an example of a very important pattern found in many different situations, a pattern called exponential decay. Figure 31.9 shows the decay graph for 3 different isotopes, each of a different rate of decay. So number of undecayed nuclei, time, you can see some of them decay very quickly, some take a very long time. So this is where half-life comes into play. Some radioactive materials decay faster than others. Although the 3 graphs look different, they all have something in common, their shape, that is exponential decay shape. They are curved lines having a special property. If you know what is meant by half-life of a radioisotope, then you will understand what is special about the shape of these curves. The half-life, this is what we use for half-life, T-half, of a radioactive isotope is the mean time taken for half of the active nuclei in a sample to decay. In a time equal to 1 half-life, the activity of the sample will also halve. This is because activity is proportional to the number of undecayed nuclei. So I mentioned about this activity. Now remember, A is equal to minus lambda n, and that minus lambda is a constant. So we can say A is proportional to n. N is the number of undecayed nuclei. This is the activity. So you learn 2 equations for activity. One is A equals minus lambda n, and the other is this one. But this here, n is different. This is equal to the number of emissions or decays. So this is the number of decays. This is the number of nuclei remaining. This is also, n is equivalent to the number of emissions or decays. Okay. It takes the same amount of time again for half of the remainder of the nuclei to decay, and a third half-life for half of the new remainder to decay. So you see, it takes the same amount of time again for half of the remainder of the nuclei to decay, and a third half-life for half of the new remainder to decay. So you see, the half-life is constant. So what this means is the third half-life for the half of the new remainder to decay. So what you can see here is, here it's 100. Now when for the 100 to become 50, it takes 1 half-life. Then the 50 to become 25, it takes the same time. You can see the same time is that half-life is the same. Then from 25, if you have this, now you see here 100 divided by 2 is 50. It takes a certain amount of time. That is the half-life. Then from 50 to 25, again you can see it takes the same amount of time. So that is again the half-life. Then 25 to 12.5, it takes the same amount of time, which is one half-life. All radioactive decay graphs have the same characteristic shape. Percentage of undecayed nuclei versus time. In principle, the graph never reaches zero. It just gets close and close. In practice, when only a few undecayed nuclei remain, the graph will cease to be a smooth curve. So you see, when only a few undecayed nuclei remain, the graph will cease to be a smooth curve because of the random nature of decay, and it will eventually reach zero. We use the idea of half-life because we cannot say when a sample will have completely decayed. Then we can write a mathematical equation for this. We can write an equation to represent the graph shown in figure 31.10. This one. Okay, so that is this equation. Okay, where n is the number of nuclei remaining, undecayed nuclei remaining. Undecayed means it's remaining. If we start with n naught, undecayed nuclei, that n naught is the starting number of radioactive nuclei or the undecayed nuclei. Then n is n that remain undecayed after time t is given by this. So this is the amount that is remaining or that is undecayed after time t. In this equation, lambda is the decay constant as before. You may also see this written like this because e, you can write it as e to the power that, or exp means e to the power. Note that you must take care with units. If lambda is in per second, lambda is the decay constant, then the time must be in seconds because the power overall should not have a unit. So if you substitute lambda in seconds, the time should also be in seconds, so that seconds cancel out. The power should not have a unit. The symbol e represents the number. Okay, so you know this e, when it is a constant, it has this value. And remember, when we use natural logarithm, there the base is e, which is the same e here. Okay, so it's a special number in the same way that pi is a special number. You will need to be able to use the e to the power x in your calculator. So you have that in your calculator. So to solve problems involving e, the activity of a sample is proportional to the number of undecayed nuclei n. So you can see here, this is the number of undecayed nuclei, and a is equal to minus lambda n. So since a is proportional to n, you see here a is proportional to n, we can replace the n's here with a and write the equation in terms of activity. So you can see here you have n, the only difference here is instead of n you have a. The activity of a sample is proportional to the number of undecayed nuclei n, hence the activity of the sample decreases exponentially. Now why is exponentially? Because e is positive, the power is a negative power. Lambda is positive, t is positive, but here the power is negative. That means if you plot a graph of a versus t, it will be an exponential decay. And by the way, you can see here it's smooth, but here you can see it's like this because that is explained here. When only few undecayed nuclei remain, the graph will cease to be a smooth curve because of the random nature of the decay, and it will eventually, finally, the graph will come to zero because all the nuclei have decayed. Okay, so these two equations are also very important. Now the next page, I have it here. Okay, so this is how you determine the half-life. If you are to determine the half-life of a radioactive substance in the lab, you need to choose something that will not decay too quickly or too slowly, because if it decays too quickly, then you can't if it was, let's say, a few seconds, then this graph will end in a few seconds. So even before you start the experiment, it has all decayed. Now if it is say 1,000 years or something like that, then this graph will be almost horizontal in the period of time you are doing it. So you have to use an isotope that has a suitable half-life. So in practice, the most suitable isotope is protactinium 234, which decays by emitting beta minus radiation. This is available in a bottle containing a solution of uranium compound, uranyl 6 nitrate, figure 31.11. So you see here, protactinium in floating layer, denser layer of uranium 6 nitrate solution. By shaking the bottle, you can separate the protactinium into the top layer of solvent in the bottle. The counter allows you to measure the decay of the protactinium. So here we have the Geiger-Müller tube connected to the counter. So that can be used to measure the decay of, allows you to measure the decay of protactinium. Practical arrangement for observing decay of protactinium. After recording the number of counts in consecutive 10-second intervals over a period of a few minutes, you can then draw a graph and use it to find the half-life of protactinium. Okay, so every 10 seconds you can see the count rate and plot a graph. Now the next example has that, so we'll go through that example. You can understand it better. Then usually we measure the corrected count rate in the lab rather than the activity of the number of undecayed nuclei. Since the count rate is a fraction of the activity, it too decreases exponentially with time. So R, remember we use the letter R for count rate. Now look at examples 7 and 8. So this is the last bit. We'll finish off with this. Suppose we start an experiment with 1 into 10 to the power 15 undecayed nuclei of an isotope for which lambda is equal to 0.02 per second. Determine the number of undecayed nuclei after 20 seconds. So again, first thing, you can write the quantities that are given in the question. So N0 is this, the initial, we start with this, and suppose undecayed nuclei of an isotope for which lambda is equal to this is the decay constant. So we are given, okay, so you can see it's written here. So we are given N0, the initial, and then initial number of radioactive nuclei, lambda, that is 0.02, and we are also given the time. We are supposed to find N. So the equation that has all those quantities is this equation right here. Yeah, so you see this has all those quantities. So N0 is the original number of undecayed nuclei, N is the number of nuclei remaining after time t, lambda is the decay constant, that's a constant, E is also a constant, it is equal to this number, it's a number like pi. So use that. N0 is given, e to the power minus lambda t, so minus lambda is minus of that, and then t is this. So after 20 seconds you will have so you can see the, remember the units have to be consistent. Here the lambda has to be in per second if you are entering the time here in seconds. So you can see here the units are already given, which are consistent units. Then simple mathematics, so you multiply this and then do this, then after that you get this. So after 20 seconds this is the number of nuclei that are remaining. Next example, and a sample initially contains 1000 undecayed nuclei of an isotope whose decay constant is this. So lambda is given, N0 is given. Draw a graph to show how the sample will decay over a period of 10 minutes. So over a period of 10 minutes. Now we know N0, again you can write down the quantities that are given, lambda is given, hence we can write the equation for this decay. Okay, so calculate the values of the number n of undecayed nuclei at intervals of 1 minute. So then you will have 10 values because this is for 10 minutes. So if you do it for every 1 minute, see 0, 1, 2, 3 like this, you can calculate the value of n when t is 1, 2, 3, 4 like that, all the way to 10 minutes. And you can see here lambda is also having the units per minute. So then minutes and minutes cancel, the power should not have a unit finally. So for it to not have a unit, both the lambda and the t have to have consistent units, which means if t is in minutes, then lambda has to be in per minute. If t is in seconds, lambda has to be having the unit per second, like that. So the units cancel out. Calculate the value of values of the number n of undecayed nuclei at intervals of 1.0 minutes, 60 seconds. This gives table. Okay, so I think this part is very clear. After that you can plot the graph, number of undecayed nuclei n versus time, radioactive decay graph. Okay, now it's very important that you answer all these questions and check the solutions at the back of the book. That will make sure you have understood the theory here very well. After you answer all these questions in the brown boxes, check the solutions, then you are in a position to answer the past paper questions. You have the minimum knowledge that is required to answer the past paper questions. So that's why whatever questions here in the brown boxes are very important. Okay, so this is the last part of this chapter, decay constant and half-life. A radioactive isotope that decays rapidly has a short half-life. Its decay constant must be large. Its decay constant must be large since the probability per unit time of an actual nucleus decaying must be high. What is the connection between the decay constant and the half-life? In a time equal to one half-life, the number of undecayed nuclei is halved. Hence the equation. This was what we learned. So after time of one half-life, so we can rearrange this like this. Then after one half-life, what has happened? The number of nuclei remaining is half the original number. So if this was 2, this will be 1, because after one half-life, what happens is the number of radioactive nuclei remaining will be half the original number. So if n0 is 1, n will be half then, so which is the same as 1 over 2. If you write half here and 1 here, and when you simplify, it's still equal to half. So we have this. Now here you can see t is t half, the half-life. Now you can rewrite this. So remember, here the power is negative, you can make it to a positive. So it will be 1 over e to the power lambda t half is equal to 1 over 2. So if you take the reciprocal on both sides, you will get this. Or simply you can flip this fraction and make this power positive. Then we use natural logarithm on both sides of this equation, ln. Then you can convert this into this. If you take natural logarithm on this side and this side, what will happen is natural logarithm has the base e. So then you can bring this power down here. These are the rules of logarithms. Okay, if you're not familiar with this, you have to review the rules of logarithms. Then you will know how to do this. So then this comes down. Then log to the base e, e is 1. So here it will be 1. So then this will be this. And here we have ln 2. Log to the base e is ln. Log to the base e is ln. So ln is log to the base e. Then we have this. Okay, so yeah, okay, so they're telling you the rule here, see. But if you are still not familiar with this, review logarithms. The half-life of an isotope and the decay constant are inversely proportional to each other. That is, yeah, so you can rewrite this. Now I showed this in the beginning. Lambda equals, this is what, ln2 divided by the half-life. ln2 is approximately this number. You see it's here, ln2, natural logarithm of 2. Thus, if we know either the half-life or decay constant, we can calculate the other. For a nuclide with a very long half-life, we might not wish to sit around waiting to measure the half-life. It is easier to determine lambda by measuring the activity. So once you measure the activity, and then you can find lambda and use that to determine the half-life. T half is the symbol for half-life. Note that the units of lambda and t half must be compatible. For example, lambda in per second and t in seconds. I explained this already. Okay, we have arrived at the end of this chapter. Now make sure you do all these questions in the brown boxes and check the solutions. That will ensure that you have the minimum knowledge required to answer the past paper questions. So once you go through the theory, go through the examples, answer all the questions in the self-assessment boxes or the brown boxes, self-assessment questions, which are the questions in the brown boxes, then you will have a good understanding of the questions in this chapter, and after that you will be able to answer the past paper questions. And make sure you do the end of chapter questions here also, and check the solutions which are given in the back of this book. Finally, we'll go through the summary to complete this whole thing. Alright, now when you go through the summary, you will have a better understanding, because I think in the beginning also normally we go through the summary to help you have an idea of what we are covering. Nuclear reactions can be represented by equations of the form. Okay, so this is representing each of them. This is representing the nucleus. This is the nitrogen nucleus, and what happens is we have beta minus decay here. So when beta minus decay occurs, what happens? neutron becomes a proton. So the proton number increases by 1, the neutron number decreases by 1, but since this is the nuclear number, which is equal to the number of protons and neutrons, that is remaining the same. Einstein's mass energy equation is equal to this, equals mc squared, relates mass changes to energy changes. Then we found the mass defect, that is the difference between the mass of the separate nucleons and that of a nucleus. The mass of the separate nucleons will be greater than the mass of the nucleus. So if you take an equal number of protons and neutrons that make up the nucleus, and if you add the individual masses of the protons and neutrons, that will be greater than the mass of the nucleus that is made up of those protons and neutrons. Atomic masses may be measured in atomic mass units. Okay, so we have 1 U, 1 atomic mass units. Sometimes textbooks use AMU also. So that is equal to this much in kilograms. Now you can see this is a very small number. So instead of that, we use this U, 1 arbitrary mass unit, AMU, atomic mass unit. The mass excess of a nuclide is the difference between its mass in U and the nuclear number. Okay, again we saw this, again very simple. Mass excess is the difference between the mass in atomic mass units and the nuclear number. Nuclear number is a whole number, but the mass in U, you can see here 1 U is equal to this much. But U, so you saw some examples. If you are not familiar, go through that. The binding energy of nucleus is the minimum energy required to break up the nucleons into separate nucleons. Okay, all the way to separate them all the way to infinity. Separate the nucleons to infinity. That also you have to mention. The binding energy per nucleon indicates the relative stability of different nuclides. Greater the binding energy, the more stable it is, because binding energy is the energy required to break up the minimum energy. So if binding energy is greater, you will need more energy to break. So that means will be more stable because you need more energy. The variation of binding energy per nucleon shows that energy is released when light nuclei undergo fusion and when heavy nuclei undergo fission. So we saw that in the graph. You saw that smaller nuclei, they are more likely to undergo fusion. Heavier nuclei means nuclei with greater mass numbers. Now here they say light and heavy, but some mark schemes do not allow these words, light and heavy. You have to say lesser mass number, greater mass number, like that. So if the mass number is very high, they are more likely to undergo fission. If the mass number is very low, like hydrogen, like that, they are more likely to undergo fusion, and both these fusion and fission release energy. The variation of binding energy per nucleon shows that energy is released when light nuclei undergo fusion and when heavier nuclei undergo fission, because these processes increase the binding energy per nucleon and hence results in more stable nuclei. So when fission or fusion occurs, the binding energy increases. And remember, iron, in that graph we saw iron had the highest binding energy. So that actually that graph is very important. Okay, maybe we can have a quick look at it again. We'll show you because it's a very important graph. Here you can see this one, iron is here. So what happens is when these undergo fusion, they give the products which are having higher binding energy, whereas these, when they fuse, what results in is elements which have again higher binding energy, and it was shown here also. See, when fission occurs, the products have greater binding energy. When fusion occurs also, the products have greater binding energy. Nuclear decay is spontaneous and random. Now I told you have to know the meanings of these words. In the exam papers they can ask you. This unpredictability means that count rates tend to fluctuate and we have to measure average quantities. The half-life T-half of a radioisotope is the mean time taken for half of the active nuclei in a sample to decay. You have to memorize the definition of half-life. It was in a highlighted green box also in the chapter, and also decay constant. You have to memorize this meaning with understanding. In the exam they can ask you to write that. The decay constant lambda is the probability that an individual nucleus will decay per unit time interval. The activity A of a sample is related to the number of undecayed nuclei in the sample n by A equals minus lambda n. The decay constant and half-life are related by the equation. So we saw lambda is equal to natural logarithm of t divided by t half. So this is how the decay constant and the half-life are related, and ln2 is approximately equal to this. Natural logarithm of 2 is ln2. We call this natural logarithm ln. We can represent the exponential decrease of a quantity by an equation of the form this. So you can see if you plot a graph of x versus t, it will be an exponential decay curve. That means x is decreasing with time, where x can be activity, count rate, or number of undecayed nuclei. So instead of x here you can write a, then a where a is the activity, a naught then will be the initial activity, a will be the activity after time t. You can replace it with r, the count rate. So if you have r here, then r naught is the initial count rate and r will be the count rate after time t. And if you have n naught will be the initial undecayed nuclei, then n will be here, n will be the undecayed nuclei after time t. Alright, so that's the end of the chapter. So make sure you do all the questions in this chapter, which will ensure that you have understood the relevant theory. Now here you can see this could be a past paper question. So that's why I told you, you answer all the questions in this chapter, check the answers, or check the solutions. The solutions and the answers are all given together for every single question here. And after you do all of that, if you have understood everything, you are in a good position to answer any past exam paper question.